I'm Randy Anderson. On behalf of the leadership here at Science, Scripture, and Reason, I'd like to welcome you to our October 2025 meeting, and we are delighted to have Dr. Brandon Reddell back with us. Brandon was here in May and spoke on the habitable zones on the Earth, and there were at least 9. He reminded us that it's not just water, but there are many other things. And now he's back to talk in a little wider scale, to look at the galaxy and see what it takes to have life in the galaxy. So, Brandon, we're delighted to have you. For those of you who don't know him, I'll give you a bio. I was going to give you a brief bio, but he doesn't have a brief bio. He's got a pretty extensive bio. He currently works at NASA Johnson Space Center in the Engineering Directorate, and he has degrees in physics from the University of Houston, a master's degree in applied space physics from Johns Hopkins University, and a PhD in physics where he specialized in high energy space physics from the University of Houston. His current work, he supports all of the human spaceflight programs in the areas of ionizing radiation effects produced by galactic cosmic radiation, solar particle events, and the trapped radiation belts around the Earth. Dr. Reddell also serves as an adjunct professor in astronomy at Los Angeles Pacific University and occasionally in the physics and astronomy at the University of Houston at Clear Lake. Additionally, he's an adjunct professor in the School of Divinity at Regent University, where he teaches cosmogony, which is the model of how the universe originates, and astronomy and design in the universe. He was actually my instructor in the Reasons to Believe Institute course, probably now 7 or 8 years ago, I don't remember, but I highly recommend the course, and he's a great teacher. Brandon's been married for 28 years to his wife Laura, and together they have a son. He's active in his church and small group leader, and a strong advocate for showing how the results of science supports the Christian worldview. He loves the outdoors. He enjoys the heavens through astronomy. He's been an astronomer in an amateur level at least for 35 years, which is pretty amazing. And he loves hiking, running, and biking. So, Brandon, we're delighted to have you here, and I'm going to turn it over to you.
Alrighty, just one quick mic check. You can hear me okay?
Yes.
Thank you. And thanks for that introduction, Randy. Time flies. I guess we're having fun. Uh, so I do want to just give you, we talked about how long I've been doing amateur astronomy. I actually just came back from an astronomy trip, and I might have a little bit of a cold or allergy, so please forgive me if I'm coughing or sneezing throughout this talk. This is meant to be, I'm happy to take questions as we go along, certainly at the end. And really, it's kind of like a part 2 of a talk. We were talking about habitability, and we're just kind of stepping out one notch further and just looking at what are other conditions that we probably should consider, when we're talking about just life and, let me share my screen here. So hopefully, are you seeing my in presentation mode?
Yes.
It's always a challenge. Okay, I have 2 screens, but okay, so yeah, so tonight just stepping back a notch, and we're looking at outside our solar system, right? We're inside of a galaxy, and so are there conditions out there, or what about our galaxy we're in, the Milky Way? Is there anything unique about our position there as well? And so here's the outline. So I talked a little bit about the motivation already, but this is part of really a series of talks. And if any of you were part of the Sacramento RTV talk I did, I know, gosh, pre-COVID, this is essentially a very similar talk. I tried to look up to see if things have changed, and for the large part, it's a lot of the same. I did update a couple things in here, but for the large part, the main emphasis of this talk, which is fascinating, is number one, just to give you a feel for our place in the universe outside our solar system and the wonders of about it. And then, of course, some of the unique features that allow a stable location for the Milky Way and for Earth. And so I'll be running, I'm not going to read all these bullets here, but we're going to kind of stroll through, we're going to step outwards to the largest scale of the universe. I do want to pause it I'm about a third of the way through and show a short video. I hope that works. But if not, I can always post that link. That's based on some computer simulations that some other folks have done that really help you visualize this. And then really just then we'll step back down and kind of talk a little bit some of the features, and then conclude with our really looking at our back down to our galaxy. And so if you remember last time, I guess maybe 6 months ago, yeah, these are the nine. Actually, there's 10 here. I threw on space weather effects. Honestly, the more we look, even RTB, reasons to believe in Houston. I mean, and sorry, reasons to believe in California. I'm in Houston. uh, you know, the deeper we dig into the universe and just to understand anything, including, let's say, biology on Earth, right? We find more and more conditions that are just very uh, precise, right? And if they're off just a little bit, things might not work the way they should, or they might not even be in place. And this is part of a broader topic that you may have heard of called fine tuning. Fine tuning is can be applied pretty much to everything in the universe that has the appearance of design, right? A lot of scientists say, "Oh, it just appears that way," but when we look at things like the constants of nature, things like that, it's inexplicable why they have the values they do, but each one uniquely. Uh, for instance, like the mass density of the universe, you may know have heard that it's fine tuned to 1 part in 10 to the 60th power, right? And so that's a one followed by 60 zeros, and so you almost have the same odds of randomly throwing a dart and hitting a specific uh, electron or proton on a star. If I picked the star and said, "Hey, hit that one proton in a star," you almost have the same odds. Not quite, but it's on the order of magnitude of that. But the point is um, these things start stacking up, and then it sort of begs the question: ultimate design in our universe. Now, I don't have a lot of scripture in here, but these are good pieces of data to explore further to help those people to understand that maybe there is purpose in design in our universe, and there's a reason um, given the time and the age of the universe and all the conditions in place, certainly seems to show that design is a better choice than chance and or necessity. And so the point, moving further after the sort of habitability of the solar system and the planet, the purpose of this presentation is, like I said before, we're going to look at our galaxy, and then the conditions in our galaxy and our local vicinity in the universe. And so I'm going to begin. I'm going to show a few slides here. I know these are small, but it's really hard to show millions of light years on a computer screen. So starting with our solar system, hopefully you can see this. This bright dot in the center is our sun. Uh, this sort of kind of a yellow circle, I believe that's the asteroid belt. So we're inside this little circle here, probably where the N is on the sun, for instance, right? And then you have Mars and Jupiter. This kind of light cloud here thing is sort of the furthest thing out in our solar system, called the Kuiper belt, or one of them. And a lot of the asteroids and things like that come out of here. And so stepping back one let's say level further. I'm not going by powers of 10. I'm just kind of going broadly in terms here. This is kind of what our galaxy looks like. Obviously, we can't go out and take a picture of it, but we know it's a barred spiral galaxy, very symmetric with symmetric spiral arms. And there's this rim here called uh, outer Cygnus arm, and we're actually on the Orion spur. This is the spur, and we're just on the edge of this thing. It's kind of debated. I've heard 2/3 or halfway, but we're probably closer to 2/3 the way out from the center of the galaxy. And so that's kind of our position on just where we are in our galaxy. And if I remember correctly, it takes, I want to say 250 to 500 million years as this thing rotates for us to do one complete orbit around the galaxy. It's quite a long time. And then stepping back one step further, our galaxy is part of what we call the local group, right? This is in astronomy. It's in any astronomy textbook. And, you've heard of the Andromeda galaxy and maybe Triangulum, right? That's actually a galaxy we were just looking at this weekend out in West Texas. You can see these as clear day. In fact, if you're out in the desert, you can see Andromeda with your eyes. I was doing that. Now, it doesn't look like this. It just looks like a gray smudge, but hey, you're looking at something that's 250 million light years or 2.5 million light years away. Um, but nevertheless, we have these are the three biggest things in our local group, but there's a lot of other galaxies, and then these little dots around these are what we call dwarf galaxies. Each of the big galaxy has smaller orbiting galaxies as well that are called dwarf galaxies, and we'll talk about those some in a little bit. Now we're kind of getting into very large size of the universe. So the local groups part of this Virgo cluster. Okay, so I'm trying to look at my screen here. uh, the Virgo cluster, it's kind of this vicinity where the red words are on this particular view. And as you can see, when you blow out to this scale, we start to see I don't know, I'm not sure how many folks here do amateur astronomy, but you may have heard of M81 and Bode's Galaxy. That's in the Big Dipper, the Sculptor group. That's out right now. There's something called NGC 253. It's a really nice galaxy that you can see that's fairly bright through a telescope, but it has a lot of nice structure in it. But you can start to see a lot of these things in our vicinity that we can see with telescope, like amateur-based telescopes. But then, and by the way, all of this is the Virgo cluster, and we're kind of like on the edge of it, right? The local group is kind of to the left here of the core of this, the bulk of this Virgo cluster. Um, and so that we'll talk about that. That's kind of helpful too for life in general. Okay. Now, again, we're trying to keep it sort of centered. So if you can see these blue words here, this is approximately where our local group is. Now we're stepped out even further, a little bit more detail. Uh, Again, you can see the Virgo cluster here, but now there's something called the Pegasus cluster on the left side here. On the far right, the Centaurus cluster, right? And so as we kind of branch out further and further, galaxies start clustering up into larger superclusters. And so there's just more and more. And then you have a local supercluster region. As you can see now, you're starting to see a lot of this clumping together. And again, we're in the Virgo supercluster at the center of the screen, essentially under where these blue words are. And so we're really close. I already mentioned like Centaurus and what was the other one? Uh, I don't think it's actually on this one, but as you can see, though, we can see a lot more clusters here. And it just goes on and on. I don't know if they have these named for everyone, but there's some of these are sort of reused from constellations, right? Like Pisces, Cetus, Perseus cluster, Ursa Major supercluster, right? But this is not to mean that the constellation Ursa Major is that way out here. That's just a name for the supercluster. Now, on a larger scale, now this isn't done by a different artist, right? But you see now this kind of web-like structure. Um, we're here in this region here. So this is where the Virgo supercluster is, or the edge of it. And it's kind of funny because it says Virgo way up here, but the label probably should be right here. But this is the core of the Virgo cluster. Um, and so this is their best way to model it. But the ground-based telescopes have done surveys, and I think I have a chart later on that shows that um, when they start mapping all these and putting them together, it makes this web-like structure. And so, excuse me, this is what they call the cosmic web. These are also called filaments, and so you may hear that terminology. And so, actually, here's where I want to pause it. Then this is a computer. This image here is based on a computer simulation. But this is what our universe looks like kind of at the largest scale. And so let me unpause. I want to go to this video here. I hope I can get this to work. I have a video. Um, there's several of these on YouTube. Where's my share button? But it's really neat because it puts some perspective on uh, what it would be like to fly through, right? We can't really do this. So let me see. Let me try to play this. I hope it works. Um, Are you guys? It, you should be seeing some text here. It's gone. Screen's gone black. Black. So what we're doing here is this is a computer simulation, but this is flying through the Virgo or through the filaments, kind of in and around the our Virgo supercluster. And so all that pink and yellow are just millions of galaxies all clumped together, right? Each bright spot is a core of a galaxy. Are y'all seeing this move? If you could just nod your head. Okay, good. Thank you. Yeah, so in this simulation, they fly around and then kind of heading back out. And there's a couple more things here. The show, this is maybe 2 minutes total. Uh, so there's a lot of math and computational power gone into show this computer simulation. And so next, this is a real time lapse, right, from the moment of the origin of the universe, the Big Bang. And so this is kind of as time goes on. That's what the Z number is. We're coming from the origin to now, and it looks like you can see bubbles separate and the filaments take shape. And so this may look like processes you might see in chemistry or something, but this on the larger scale, all these white lines here are the clustering of filaments. And then finally, yeah, this is just another simulation of a chunk of the universe. But in all directions, this is kind of what it looks like. And I think, oh yeah, this is where the observations are from ground-based telescopes. In case you're wondering if they're making this up, these are real images, right? Put together over lots of surveys using um, ground-based and satellite-based measurements. And so when they start plotting all the galaxies at the right ascension and declination, and so if you put all those things together, um, hold on a second. So, anyways, hopefully that was great to see that. I'm going to go back to my presentation. Give me a second. So that's what the large scale structure of the universe looks like. And um, if you can nod, if you just see if you can see it. All right, thank you. We made it without a hitch. So yeah, filaments and cosmic. Okay, so now let's kind of go back and look at some of these individually. Now this is another view, right? You can look on the computer. A lot of people spend a lot of time putting these models together, and there's really cool pictures. This is just a different perspective, kind of a spherical kind of view. Again, it's maybe hard for you to see. There's a blue kind of grid on here, and it's centered on us, right? So we're on the edge of this Virgo cluster. And what I have highlighted here is so the Virgo cluster is part of um, something called the Laniakea cluster, supercluster, right? So at this point, it might sound like semantics. Just when you have us and our nearby clusters kind of clumped together, that forms one bigger supercluster. And so, right, we have the Pavo Indus supercluster, the Centaurus and Virgo and Hydra. That all of these make up Hydra, Laniakea. And so here I'm zoomed in at the center. Um, uh, so maybe you can just get a little bit of feel. If you again keep an eye on this bullseye here where the blue central lines cross. Now it's kind of hard to tell, but we're kind of like on the edge of this Virgo cluster, and that's important. We'll talk about that in a minute. Here's another view. This is color coded, and basically the more green it is, like not aqua green, but like real green. Hopefully the colors are showing up. The more green it is kind of the more bit denser stars. And in this particular view, as again, you can see we're on the very edge of the Virgo cluster. And so um, this is important because do you, if we're in the center of what kinds of things can you imagine happening for a galaxy located in a very dense region, right? If our Milky Way might be 12, let's say 12 billion years old or something like that, over the 12 billion years, right, if you're in a very dense part of the supercluster, you're going to have lots of encounters with other galaxies, and so those are very disruptive. You certainly can't have a stable galaxy, one that can keep conditions on individual planets eventually, right, if you're interacting with other galaxies. So our Virgo supercluster, right, which is part of Laniakea, it's about 110 million years or million light years across. Just for comparison, our Milky Way galaxy is 100,000 light years across. So we're a like 1,000 times bigger than that, right? Thousand size the Milky Way galaxy. And so in this particular picture are some distances, and you can find all this information. This is sort of common knowledge, but again, the local groups here in the center, and just to give you some perspective of the vastness of space, right? You look, the M66 group is 35 million light years away from the local group. The core of the Virgo cluster is 65 million light years. Draco group, you may have heard, the M101 group and all we're talking tens of millions of light years for our closest neighbors. And so, uh, for something to be considered a galaxy group, you need or a cluster, excuse me, for a cluster you need 100 different or at least 100 galaxy groups to make up a cluster, and you need so many galaxies to make up a galaxy group. So as you can see, there's a very weird hierarchy here. Galaxy groups are groups of galaxies of at least 50 or more. And we're really talking about the big ones. We're not talking about dwarf galaxies. Whereas clusters are groups of hundreds of thousands of galaxies. And so that's why you see in order to see that, you have to kind of step back, and that's where you start seeing the filaments sort of starting to develop. Um, so for the takeaway from this particular slide is even in our own supercluster, the Virgo supercluster, there's still quite a bit of space between our our local group and our nearest neighbors. Now, this is a real picture from the Hubble on Able 2537. You can actually see some Einstein rings in here. But this is a galaxy cluster. In fact, this past weekend, I don't have pictures to show, but I was trying to use an 8-inch telescope to look at some of these that you can see, as amateur astronomers, you can see some of these things. Maybe not in this detail, but you can see quarters of these galaxies. Now, galaxy clusters, as we just talked about, contain several thousand galaxies, many only separated by a few diameters, right? When you look at there's lots of pictures of, if you go to look at the Able galaxy clusters, Able is like a catalog. You start to see a lot of them are look fairly close together, right? All these galaxies in here are very close. They can contain, um, when you start adding up all the stars in here, a lot of times astronomers they did, they don't really go by physical size. They usually talk it in terms of mass relative to our sun or our Milky Way. And so when we're talking about clusters of galaxy, we're talking about 10 to 1,000 times the mass of the Milky Way. And so clearly, because of gravity, if you're in one of these galaxies, right, depending on how dense it is, you're gonna feel the effects of gravity over time, and that could affect life on Earth if Earth is in one of these type of galaxies, right? Life on any of these planets in here. Most galaxies are located in very rich clusters. That's kind of what the point of on the last slide is. But there's three problems that come with that. Here's a particular group called the Higgs. So the Higgs and compact groups are, again, galaxy clusters. This is a really pretty picture from Hubble. Um, Higgs and compact groups are I think it's like four or more that are really tightly close together. But look at these five galaxies, right? They're very compact in here. Now, when you're this close, there's at least three problems, right, that are well documented. Obviously, drifting around close to each other, you have the potential for collisions and mergers. There's another feature called ram pressure stripping, where these close encounters, basically swipe the gas right out of some galaxy, and it's the gas and dust that condense to make the stars. And so that stuff's needed to keep a spiral galaxy going. And I'll talk about that a little bit at the end. But you have to have an constant infusion of dust and gas to keep a spiral structure going. And so certainly that would be a problem. Then the tighter, gravity is constantly pulling these together. And so the tighter they are, the more gravity wants to pull them closer in. And so that affects the lifetime of the galaxies as well. And so for habitability, some of the things we need to consider is, you know, we're talking about habitability on a planet, right? So the galaxy you're in must be must be distant from large close by neighbors and from cluster cores. And that's kind of really the sum to avoid these three features here. And it's probably definitely more. Uh, Now, when we look at our local group, I guess we're kind of stepping back down, right? We want to be on the edge of a galaxy, on a cluster, uh, away from the core of like a whole density of it, right? We want to be on the inside the cluster. You want to be on the periphery if you can. And then if you're in that location, like we are in our Virgo cluster, um, the question now is, do we have an unusual Virgo, like is our Virgo cluster a little bit unusual, or our position in it? And so one thing we know, uh, this picture here on the right is kind of like a blown up version of this section here. So this red text here, this bright thing next to the red is our Milky Way galaxy. Do, if you look on this picture, right, this is relative scales here. Andromeda is way over here, and that's our nearest neighbor that's large. Now there are some small ones in here. These are the dwarf galaxies, but we need to have you know lots of dwarf galaxies which affect how spirals behave over long periods of time, but we also want to be separated from our nearest neighbors for a certain amount of time. So you may have heard that the Milky Way and the Andromeda is on a collision course, right? I think it's 2.5 million or 5 million years. I think it's the prediction about the same time our sun might go red dwarf. But these two galaxies, gravity is pulling these two to each other, right? So um, that distance makes a certain amount of time for life to happen on Earth, right? And to develop it. even if evolution, if we're talking about evolution and things like that, that needs a lot of time to develop. And so if Andromeda was much closer, that's a problem on those given timescales. Uh, Milky Way has, you know, two very bright uh, dwarf galaxies, but it actually has a couple like tens to hundreds over its lifetime. But if you have ever been in the southern hemisphere, you may have heard of the Large and Small Magellanic Clouds. Those are actually dwarf galaxies, and you can see those with and if you're out in the darkness in the southern hemisphere, you can see those up in the sky. Certainly, you can take pictures of them, but this is what they look like. This is a real image. That's the small on the left side and the large. They're respectively 160,000 and 200,000 light years away from the center of the Milky Way, or from us, I should say. Now, they look big, but because they're close, they're not quite as big as looking at another full up galaxy. These are only 14,000 and 7,000 light years across. Remember, the Milky Way itself is 100,000 light years, so these are pretty small, but these are the largest of the satellite galaxies. So there was a paper, and I tried to find an update on this. I talked about this a long time ago, I think, but in 2011, this guy, this this team of folks looked at the time all the data for over 200,000 galaxies, and of those, they identified 22,000 or so that had a similar luminosity as the Milky Way galaxy. Okay, luminosity is just energy output. You can think of it as brightness. Of those 22,000, uh, only 3.5% of those galaxies have two large galaxies similar to the Large and Small Magellanic Clouds, but 81% had no large dwarf galaxies. Um, so that's just sort of a statement of fact. Now, when astronomers do galactic models looking at the evolution, over time of a set of a spiral galaxy's lifetime, uh, there has to be a constant sort, right? These things are spiraling in, and it has to pull gas and dust into the arms because that's where new stars are formed, right? They're formed from the gas and dust condensing, and so without that, you don't get star formation. And so the number of large galaxies, like the Large and Small Magellanic Clouds, they help stabilize that. But you need a lot of the small ones too, that have this sort of constant supply over billions of years. Um, if you have too many, I didn't see the number on, like, it's not a lot that have a lot more, but too many will be disruptive to the Milky Way. And at the very end, I talk about we have good evidence looking at Andromeda where that's been a problem. And so I'll share that too at the end. So we've kind of talked a little bit about the Virgo cluster and then Laniakea, the Virgo cluster, local group, right? And then our Milky Way itself. Is the Milky Way first of all, what type of galaxy is it? And then, is there what's unique about that and our place in it? So we're kind of getting more localized, if you will, and we have a lot more information now as we get to closer to home, so to speak. You may have seen this as diagram. Sometimes it looks like a tuning fork. This is just in astronomy, they call it Hubble's classification. And so the E galaxies are elliptical. And then what I don't show on here are lenticular galaxies. They're kind of a strange breed, but they mix these ellipticals kind of with they look kind of like spirals, but you don't see spiral arms in them. But in this particular case, you have ellipticals, and then you have two branches of spiral galaxies. You have the barred spirals and then normal spirals. Okay. And then way here on the other right are irregular galaxies. And so they have a lot of more, they're like younger, but chaotic, have some star formation. The ellipticals on the far left are older stars. They look kind of like a just like a cloud almost, very chaotic, but really no new star formation, and they're older. And then with spirals, you kind of have a mixed bag of various kinds. But the spiral, our Milky Way is one of these barred spiral types. I think it's the SBA or B. I think there's some debate on that too. Um, where's my page now? So the elliptical galaxies. Here's a zoomed in picture of IC 2006. Um, so in astronomy, when they talk about metallicity or metals, they're talking about elements higher than hydrogen and maybe helium, right? They're just talking about like stars are pretty. The older stars, and bigger ones can produce carbon and oxygen and iron and so forth. Anyways, those terms in astronomy, it's not like physical metals, right? They're talking about just higher elements on the periodic table. But these have hardly any of the metals, the heavier elements. There's no structure that can be seen. Um, they Most of the stars are late in their lifetime, and so just in general, if you're looking for life out there, you can't expect to find uh, stable systems here because number one, there's no constant and safe structure here, right? Orbits are chaotic. They're randomly, they're not orbiting anything, right? So that's a problem. Stars are too old, and probably lots of collisions and things like that. So we're not really would expect to find any, if at all, planets in these types of galaxies. Same thing with the regulars. They don't have the irregular shape. They're kind of all over the place, chaotic in appearance in the same sense. They're usually pretty small. They're usually found to be closer to larger galaxies where they often interact, and that's why they get some of these funny shapes. But they do contain lots of gas and dust, and because this looks bluer, usually they have like little sections of blue and reds, right? There are places of star formation, but um, they're not stable locations because not only they do the interaction, but they're not, they're chaotic orbits. So stars are interacting with other stars in this galaxy and so forth. On top of that, because of the irregularities, you have high levels of radiation exposure, and the like a spiral has a core, and it can retain a lot of the heavy elements. That's important when you have planetary formation. But because we don't have a core here in these type of galaxies, even though you have star formation, we're not expecting to see a lot of the heavy elements that you would expect for that are necessary for life. Now, when we talk about spiral galaxies, here's kind of a schematic just to help orient you a little bit. Um, we're mainly an exoplanet research. Obviously, we're only mainly looking here in our galaxy, but I think they've found a few out in other spiral galaxies, exoplanets. Um, you have not only do you have a core of a galaxy, okay. If you were to take this left side and kind of rotate it over edge on, this is kind of what it looks like. It has a certain thickness to it. Our It could be 400 light years, I think, up to 2,000. I think our Milky Way is probably around 1,000 or so. It's active area of research. It's hard to really measure that, but you do have the core of the galaxy, and then all these dots here on the outside are globular clusters. They're just pockets of where gas has condensed and formed lots of stars, so they're all sort of gravitationally bound, and you can easily go out and see those out in amateur astronomy. It's kind of nice, but the point is, our galaxy is about 100,000 light years. Solar system is about 26,000 light years from the center. you have this sort of nuclear bulge here. Now we now know at the center of our galaxy is a supermassive black hole. They're finding that's probably the case in most of them. You know, gravity is always an attractive force. So as stars get pulled in towards the center, right, you create black holes that way. And uh, if we're out on the edge and we're near the center, if you're trying to look uh, away from the center, if you're trying to look towards the center, right, that's really hard to see because you have a lot of gas and dust to look through. Whereas if you're looking off axis, you got free space to look at, and so that's um, kind of nice with unique spiral arm structure because you get there's some stability that comes with that, especially if you're in and around the arms. What is special about the Milky Way? Often it may be called a green galaxy. Now, it doesn't mean literally green in color. If you saw them, when I was showing that picture of star formation regions, they typically look blue, right? And the nice thing is when you have a lot of young stars that are blue mixed with sort of middle-aged stars, which are yellow, right? From a distance, blue and yellow kind of average out to greenish, right? And so that's what they mean by green. It just means a galaxy containing a lot of blue stars and middle-aged stars, but like our sun. Our sun's a yellow star. Now, a galaxy dominated by blue stars, right? If there's too many blue stars, they're very active. So they're putting out lots of intense flares and X-ray radiation. Um, uh, some that are where gravity is really working in overtime have aggressive star formation, and so that leads to there's a lot of energy input and output, and that changes the dynamics of spiral arms for where these stars are located. Um, on the other hand, if you have older stars, I don't know if you remember from the last talk, but older stars and younger or M dwarfs and older stars tend to be red. So a galaxy dominated by red stars, which are also bathed in radiation. Uh, M dwarfs are 100 to 1,000 times more massive than our G-type star of our sun. And by the way, 75% of all the stars on the main sequence are M dwarfs. And so a galaxy that for some reason might have mostly small stars will look red and be very, very challenging for life's conditions for two reasons: radiation, and then uh, it says also lack of necessary level of ongoing star formation to sustain the spiral structure. Any questions so far? Just let me pause there for a second. Okay. And if we have somebody who can talk here at the end. Uh, Another interesting thing about our Milky Way galaxy is, uh, again, this is from this paper here. It's maybe about 20 years old now, but comparing the Milky Way to lots of other galaxies, we find that the Milky Way is what we call underluminous, right? And that's seen on this graph here. Like this sort of central line is kind of like the average. The dotted lines are the 1 sigma line. But the point is we're not quite as average as the average luminosity for this size. We're just a little bit under. Remember, luminosity is energy output. There's other deficiencies such as the stellar mass and its disk radius as compared to other stars of similar um, types, like the spiral type that the Milky Way is. One thing that they found out is that 7% of all the spirals in the local universe are similar to the Milky Way with respect to K-band magnitude, circular velocity, and disk scale length. So um, that's just looking at the fainter stars versus brighter young star formation. The point here is when you look at all the types of spirals, right? We know ellipticals aren't the same as and irregulars aren't the same as Milky Way or like a spiral galaxy. So you can only look at the spirals, and only about 7% of all the galaxies that are away from like center of clusters, only 7% of spirals look like our Milky Way in general. So that kind of eliminates a lot of galaxies, right? You may have heard that there's trillions of galaxies out there, but not all of them can host life. Uh, Most of them can't. And then finally, this is an infrared image of Andromeda galaxy. Okay. Now, uh, it's also known, Andromeda is known as M31 in the Messier catalog. When they look at so, when you look at galaxies through either infrared light or ultraviolet light, right, you see other more features that you just can't see through observation because gas and dust block our view. But what they look at, this is from a paper listed down here, and I have them all listed at the back. There's two spiral structures here in the Andromeda galaxy, right? You have this very large one going around the outside with spiral arms, just like our Milky Way. But then there's an inner one. And so this little box here inset is a zoomed in picture of the inner ring. And so this is evidence of major galactic merger with Andromeda, right? And so, as you can imagine, these things, something spiral around here, this smaller inner ring interacting with this larger ring creates instability. Now, it's not instantaneous, but over the time it would be required for life to be um, conditions for life, right? That provides instabilities, and it's probably not a good location. That's what I mean here. It's not a candidate for or stable location for long periods of times. Even the authors indicate that galaxies like Andromeda is a much better representative of the typical spiral galaxy. Most of the ones they see out there, okay, of those 7%, most of them have evidence of mergers. That's the point. Um, by comparison, okay, the Milky Way galaxy has, and this is from what the author has said, an extremely quiet merger history with no accretion of objects, like meaning galaxies or clusters, more than 10 a billion solar masses in the last 10 billion years. And so that's important because as far as we know, uh, if the universe is only 13.7 billion years old, Earth and our solar system, our sun, right? We're 5 billion years, right? It has a 10 billion year lifetime. We think, that means our Earth was formed along with our solar system when the universe was only about 9 billion years ago. So there's not a whole lot of time for any kind of system. Um, if life's representative on Earth, how we would expect to see it in other galaxies, there's just not a lot of time uh, of stability in a galaxy like this because these interactions, it depends on the rotation rate and how often. If it's anywhere like what the Milky Way is that orbits every 500 million years or something like that, you have quite a bit of interactions over the course of 10 billion years, and so that's very disruptive to having a stable system.
Hey, Brandon, I got a question. Do we know when how long ago that collision on Andromeda would have happened?
Uh, I don't. Yeah, I think it might be in the paper, but I think I don't know it off the top of my head. But if Andromeda, let's just say the Andromeda is like the Milky Way, which I think they believe is around 12 billion years or so, right? It probably would have happened in the early days because when we look at the Andromeda now, it looks fairly stable, like until you look at an image like this in the infrared. So it's had a lot of time to sort of uh, wind down, if you will. But there's definitely the evidence of these two spiral rings. So we know it's not in recent history. So it's probably more likely earlier on. Uh, But yeah, we could go to that paper to look. That's probably and my guess. There's a lot of they can. I don't know how well the simulations are, but they could try to simulate it and work it backwards. But I haven't seen a paper like that produced. But that could be a topic that some graduate student might be working on. That's a good question, though. The key thing, though, is yeah, we do not see this in the Milky Way. Uh, so inside our Milky Way, so this is sort of an kind of overlapping now with some of the topics we talked about last time on why we have those conditions. So this is just an artist rendition of kind of like looking what we think our galaxy looks like, face on. We have our galaxy has very unique and stable looking spiralar arms, right? They're spaced very symmetrically. You don't see that with a lot of galaxies, spirals. Remember, we're only talking about of the 7% of the spirals. Of all the spirals, look like something like this. The Again, getting back to the green and blue and yellow stars, right? It's dominated by yellow stars, complemented by significant populations of blue stars. And you can see that if you look at any image online of the Milky Way, and you can see this in other galaxies, look for the bright blue regions, right? But then look at how symmetric are those spiral arms. Um, uh, so there are some that look like that. I'm not saying there aren't any. There's no evidence of merger for at least 10 billion years. I took this from Hugh Ross's book. Some of these facts. He's an astronomer, but I think Andromeda that probably happened in the first 2 billion years of its age is why we're saying that. Um, the Milky Way has a lot of dwarf galaxies that's provided a steady uh, influx of gas and dust um, uh, that allows the star formation in our own galaxy. Now, there's something called the co-rotation radius, and that's this circle here in black. If you're low, if imagine this is a disk that's spinning, right? If you're on the black line, you're spinning at the same speed the arms are rotating around. So your position is constant relative to the arms around you, right? The second, if you're closer in to this distance, right? Think of an ice skater spinning and they bring their arms in, right? They spin faster, right? So as you come in, right, that's this conservation of angular momentum. If our sun was located, let's say, halfway between here and the core, it's going to be moving a lot faster than the arms are moving. And so we would be sweeping through these arms, and that would be very disruptive for our solar system. So likewise, if we're on the other side, right, we're going really slow compared to the arms, and then the arms are moving past us. And so it just so happens the Milky Way is right on the inside of the co-rotation radius. Uh, and that's, you know, interesting. I'll just put it that way. I mean, we have lots of planets, and we've already found what 5,500, but none of them are at the co-rotation radius. Now, it doesn't mean there aren't any that are there, but like I said, if you start stacking a lot of these features plus all the ones we talked about last time, it really starts building a really interesting case of there's something special about this world we live on. At the co-rotation radius, this is important too. It's not merely just the rotational dynamics, but that's what the first bullet says here, right? The passing of the spiral arms, right? So we want to be stable with respect to that. Um, but if you're too close to the center of the galaxy, you get too much radiation, but you need enough that you don't want to be all the way on the outside because you need a certain amount of those heavy elements to have planets. And so this is a plot, this white graph here on the bottom, the metallicity level. it's just in arbitrary units here. Uh, it has a peak around 4 kiloparsecs. Okay, remember we're out around 8 point something right? A parsec is 3.2 light years or so. We're right. I think we're 8 point something kiloparsecs from the center of the galaxy. If we were located, at 4, we would get. I can't remember if this is logarithmic scale, but I think we'd be getting like 2 to 5 times more radiation or heavy elements than we would plus the radiation. So the question is, uh, um, not why you're. So we're at this local minimum here. So the question is, you have to look at the metallicity in our solar system and Earth, right? The elements, the amount of iron, carbon, oxygen, and all those things. Now, another talk that I've done is we have an abundance of those elements. So that implies that we were actually formed closer in, and then somehow we currently orbit at the co-rotation radius. And so there's some unique things going on with our planet that uh, you know are kind of not what you would expect from natural laws, let's say. But the point is here you have to for the right amount of there's an optimum location for metallicity, just like there is for rotational dynamics. And so we're right at the optimum location now. And then finally, we orbit in this plane. But just like most things that orbit, right, there's variations. And so that's what this little green squiggly line is, right? Um, there it is. Yeah, 230 million years. I said 500 earlier, but yeah, it takes about 230 million years for our solar system to go around. Uh, we're moving it. That's where I got that number from. 514,000 miles per hour. That's how fast we're moving around the center of our galaxy. Now, the disk is about 1,000 light years thick, and our orbit kind of fluctuates over the course of the whole orbit. Sometimes we move through the plane of the Milky Way, and then we're back down, but we don't. Uh, it's not a whole lot that we fluctuate. Most stars move up and down on an average of about 400 light years in there, and we're closer to about half that. And so um, there are actual studies that look at when we cross through the plane of the Milky Way and correlating that with mass extinction events. So there could be some link there. That's not really, I don't want to go into that here, but that is a topic that people have looked at uh, because that happens several different times on the course of a single orbit. Um, so when you're too close to the center, right, there's a lot more dust in the center of the plane. So there's variations in shielding from the dust you get, and when you're at the peak and valley versus the average. But those things need to be considered when you're looking at stability over billions of years. All right, so this is my last slide, and we can talk about questions. I try to put all these things on one chart because I know there's a lot of concepts here. Now, nothing as specific as the the look the from the last talk. But when we look at our galaxy and our position in the universe within the galaxy, right, we find numerous conditions that combine to provide a location free of collisions, interference over long periods of time, but at the same time also protecting us from radiation. And some of these things I bulletized here. These are really the summary from all these previous charts, right? A galaxy's got to be in a stable location for billions of years, in an isolated supercluster, right? If you're in the middle of a supercluster, the interactions are gonna you can't survive those over a period of 10 billion years. Being near the edge gives you the best location from gravitational uh, disturbances. The same thing, most galaxy clusters are rich, and so if you're going to look for a galaxy, you want to look for one that's not in a rich cluster, kind of out on the periphery, the right local neighborhood. I'm just going down here. Uh, you want to. This is like along with the whole collision theme, right? We want a low number of large neighbors, and we want large separation distances because gravity is going to eventually pull these things together. You need a galaxy with a lot of dwarf galaxies to provide an infusion of gas and dust so that you have a lot of star formation. Um, and then having two sort of larger dwarfs help modulate and sort of manage the infusion of gas, right? And that they find that unique with our galaxy. Now then there's the right type of galaxy. Elliptical and irregular galaxies are not good. You need something symmetric that's stable for long periods of time. And so you look at spiral galaxies, and only 7% of all the spirals, um, are kind of like the Milky Way. And so in those, you want to find what we call green galaxies, right? Green spirals that have a lot of young star formation, but also middle-aged stars. And then, of course, inside the galaxy, being near the co-rotation radius is the only place, for billions of years that you can really have a stable location, free of radiation, and the right metallicity to have stable life in a solar system. You know, uh, Also at this co-rotation distance, right? You're missing out on interactions of the spiral arms and so forth. And yeah, I think that's all I wanted to say tonight. So I know it's a lot of info, but hopefully you got a feel not only about our position in the universe, the large scale, but there are really a lot of factors compounded with the previous talk that really show, makes you wonder about conditions for life. Thank you.
Very good.
Any
Thank you,
questions?
Brandon. Camera in the right direction here.
That's fine.
Find me. That's right.
And I can take questions on that or, any of the stuff, if you have questions about NASA or whatever, what's happening. Since I'm furloughed, I have more time.
One question I have, Brandon, and that is, you mentioned to be, I think you said near the co-rotation rate, that if you're right at the co-rotation rate, there's a resonance issue. And does that kick you out of that place, or
Yeah.
or
I
what's
think
the disadvantage?
the disadvantage of being right at the co-location.
Yes,
Yeah.
co-rotation rate.
Yeah, I think it's just as you said, just like when it's actually kind of a parallel, an analogy of our own solar system. When you have objects rotating around, given the force of gravity interacting, over the cycle, you get pulls and tugs, and when you get into this resonance condition, right, you're gonna get one pass, it's gonna just give you too strong of a push, and it'll push you in and out of of the um the position where you're at, right, and so potentially it could push you far enough into the arms where you're exposed to the passing of the dust and nearby stars, so to speak. So I don't know if anyone's actually looked. I believe we're on the inside of the co-rotation distance, right? Like I mean, it's not. I don't think anyone can measure it exactly because we don't have all the data, but it's not like we're down to the 100 meters away from it, right? But I think we're really close to it, but just on the inside. And so I think when you're on the outside, you eventually you start drifting outwards also.
Okay, thank you. Question?
Yeah.
Tim?
I was always told that the Andromeda Galaxy was our closest neighbor, our closest galaxy. But it would appear that what that really means is the Andromeda Galaxy is our closest spiral neighbor. Is that correct?
Yeah.
Okay.
Yes. Yeah,
Okay,
because the large and small Magellanic Clouds are irregular dwarf galaxies, right? So they're close, a lot closer, but they're not, spiral galaxies.
so how close is the closest galaxy to
I
Earth?
think let me I think did I have the distance on here? I tried to put the distance. Let me go back it up here. Where's it at? Um, I think it was 7,000 light years or 14,000.
Yeah, 7 to 14.
Is that what I had?
Yeah.
It's kind of hard to see here. Where'd it go? Yeah, it's like tens of thousands of light years. Yeah, here they go. Oh, no, that's the size of them. I'm trying to remember off the top of my head, but they're fairly close because they're considered dwarfs. Um,
Well, your first bullet item, I think, might have had it there, Brandon.
yeah, I'm gonna look up real quick on the internet here. But it says 158,000 light years from here to the large. Yeah. So that's right, 160. I just want to make sure I had the right numbers.
Yeah.
160,000 and 200,000. And they orbit, right? And so there's some variation to those as well. Any other questions?
Oh, yeah.
Yeah, I have one. Well, first, thank you. This is excellent, really interesting.
You're welcome.
What is the thought or the estimate of how thoroughly we have maybe mapped our universe? When you say around 7% of the galaxies sort of have the same spiral structure, et cetera, that the conditions
Yeah.
where we are. I mean, how confident are we that how much do we think we know?
Yeah, that's a good question. Because I mean, to really ultimately answer that, you'd actually have to know everything, right? So the underlying assumption is the universe is homogeneous in a sense, like the galaxy distributions that we measure is really the same everywhere. Uh, and there is evidence to support that when they look at like the cosmic microwave background and the temperature profile, but that is an assumption. And so, I there could be some updates to that paper, but I don't think I couldn't find any, so I don't think it's really changed much, but uh, they could update those numbers based on because there's been a few other large surveys since then that could add more statistics to that number. Um, I've read the McDonald Observatory put out another like a lab for students, and I was kind of looking at that, and it had similar numbers, but yeah, with the assumption that the local universe looks the same everywhere, right? That's kind of it's just a percent, right? And so that's what they're seeing is now that was a percent based on a couple factors here: the luminosity, the number of in this case, it depends what statistic we're looking at. Uh, this 22,000 was just purely based on luminosity. And so remember, luminosity is total energy output. And so uh, if you had a Milky Way that had a lot of red stars in it, right, they're less luminous than blue stars or young stars. And so, anyways, that kind of tells you a little bit. But yeah, that's a good question. There is not a number that I know of. I mean, so they're always trying to refine these, and with these larger surveys out there, they should be able to eventually hone in on that a little bit better. But with 22,000 out of 200, and then doing the statistics, definitely have enough to have a statistically significant. I don't know how many sigmas were out on these that are quoted here, though. I don't think they put that in the paper. Good question.
Thank you.
You mentioned radioactivity a number of times. I was just wondering to expand on that a little bit further, and also maybe even in our own area, the planets that we see. in conjunction with Earth. I just wondered how Earth fits into those and the radioactivity.
Well, so when I was talking about radioactivity in the context of like a position in our galaxy, so there's in our galaxy, there's a supermassive black hole at the center. They have jets of energy coming out of them. Usually they're perpendicular to the planes, but nevertheless, you have a lot of stars ending their life at that point, right? They're pulled in through the gravity, but um, you have a lot more large scale sort of destruction of stars, if you will. And so there's more gas and dust and things like that. And with the high energies, there's things like a lot more like gamma rays, uh, more ultraviolet radiation, potentially more supernovas and things like that. And so you have a more of a flux of that stuff being pushed out of the center. Whereas if you're way out on the spiral arm somewhere further out, right, you don't have the same kind of dynamics happening. And so that's all I was saying is if you're too far out, you're not receiving. You need to receive just the right amount of that in order to sustain life. Like if you don't have enough of that, particularly the metallicity, right, you're never going to have a solar system with the right enough of the heavy elements in it. Um, And then like radioactivity within our own solar system, right? I think I talked about this last time, you need a G-type star. Uh, if you look up the main sequence, it's pretty well known that it's roughly around 75% of these M dwarfs, and there's a gazillion papers out there. We can measure X-ray production on some of these M dwarfs, and they're measured at 100 to 1,000 times more active stars than our own sun. So you think of like these X-class flares and things like we have, you're gonna have 1,000 times more of those, like on these M dwarfs. And so the problem with M dwarfs too is they're so small that the water habitable zone, right? They're really close to the planet, like inside relative to our galaxy, it'd be like inside the orbit of Mercury. All the planets would have to be inside, or the habitable zone planets would have to be that close behind a star in within a star system that's 1,000 times more active. And so there's a lot of papers out there that um, discuss that because that that's too much radiation that's required for life. You need a little bit like cellular processes. So there's a little bit that requires some UV light and energy, but not the amount you get from an M dwarf, like being that close. So that's the other side of it. Like that's two different kind of conditions where it's like basically if you're too close, there's too much radiation. If you're too far, you're not getting enough. It's kind of like that Goldilocks thing. And those could be habitable zones, conditions, let's say, right? That you have to consider with all those other factors. I don't know if that did that answer you?
Pretty much, yeah, yeah. I was just surprised how much radioactivity the zones they were
Yeah.
in came up, and I thought that was an interesting part of your talk too, as well.
Yeah. Well, in space, like, and so that, like, that's one of the long poles for human space flight is,
Yep, exactly.
I mean, it's not, if you're in there, like a lot of the conspiracy theories, people say, hey, we've never been through the Van Allen belts. Well, the station people fly through it 7 times a day. So, um, the problem is if the sun hiccups and has a burst, right? That's really the scary part. But if you're doing long duration travel, it's that background radiation, galactic cosmic ray that's coming into our solar system from all the stars in the universe over time. And that's really low level, but it's a constant and you can't shield it. It's very high energy. You can't shield it. Yeah.
And one more question somebody asked me a couple days ago too, and it was maybe it's a dumb question, I don't know, but what's beyond the universe?
God.
Okay.
Yeah. Actually, nobody knows, right? I mean, in Big Bang Theory, they don't make the model itself is really good about describing once the universe started with a set of initial conditions. you can run it all on a computer and generate what our universe looks like, but you have to give it initial inputs. You have to give it the laws of nature. You have to give it initial mass and energy, and you start the clock, right? That's the Big Bang, right? The clock starts, and then you get a universe like ours. But the model itself doesn't know, like, that's an active area of research, right? Maybe we're in a multiverse where we're just a bubble universe in a bigger field where there's a lot more bubble universes, but um, that's a lot of physicists are arguing about that right now, saying that that's not good science or testable. So more to be seen there.
Hey, Brandon, you were talking about the co-rotation rate, and that's always confused me because what it's saying is that, like, say the sun is going at a certain speed going around, but the arms are going at a different speed, but isn't the sun part of the arm? I mean, I don't understand how that works.
So yeah, if you it's kind of hard to describe. If you so spiral arms follow. They follow. They're called density waves. And they propagate at different rates, and so the arms are waves that like push through these. I think it's called spiral wave theory, and there's actually a couple models out there, and they're trying to understand that more. That's different than like a, a star rotating around a core, right? That's just a physical object, like a planet going around the sun or something, right? That that motion's different than the density wave, the spiral arm structure, even though
So,
there's physical
so
matter in it.
Brandon, when they show pictures of the spiral galaxy, though, you got the white and then or blue, whatever. But I always thought that the spiral arms were representative of a bunch of stars. But you're saying that it's not. In other words, I guess
No,
when you talk about the waves, but the waves aren't the arms, right? I mean, waves they don't shed light. I mean, they don't, right? I mean,
yeah,
what am I missing?
yeah, that's what I'm trying to say is the I'm trying to think of how to put it in a different the when you look at I'm trying to think of the term. There was a it's called spiral density wave theory, right? Um, it has to do with the compression of. I wish I could show this slide here. Let me show. Um, I found this. Let me unshare this and show one thing. This might help explain it. It's actually kind of complicated. Oh, where's that share button here? Um, I took this. This is a snippet from trying to explain that a little bit. This. Let me know if you see this.
Hold on. Yeah, we're seeing it.
Yeah. Um, so I'll let you read through these bubbles here, Katie, if you can read them. But so now this is just theory right now. But it's people are trying to understand this. This has nothing to do with like dark matter or anything, as far as I know. But what happens is um, if you've seen these arms are tied to the waves, but there's compression uh on one side. That's what these bubbles are showing. Now this is actually aimed at showing how stars are formed, but as you can see, the bubbles seem to move based on um the passage of these arms in there's like a compression and expansion on each side. And so um now, further in, like I think all the arms are moving on the same wave, right? And so the whole arm is moving at the same speed, if that makes sense, right? Even though, uh, like if you're inside, right, let's say we're inside like, I can't show it on this plot here, but if you're inside the co-rotation radius, while you're moving, the physical object's moving faster than the wave in the inside. So you're gonna pass through. It's like the inverse, right? I tried to explain that earlier, but um, I think if you look on YouTube, you can see some models, and you can see how the wave it has to do with it being constant, and then there's a compression and expansion, and depending on if you're at this co-rotation on the inside or outside, they'll put an object there, and you can see how it moves relative to the arm itself. So I don't know if that helps. That it's actually a pretty complicated process, and I think they're still actually studying it, mostly in the context of star formation, right? They definitely know there's a compression of gas which accelerates star formation. Um, but remember, a lot of the arms are just waves of gas going through. It's kind of like I'm not sure if any of you guys have worked in the plasma world, but there's like just like you can have what's the term? Um, I'm drawing a blank right now, but there's a you can have faster than light travel like through phase systems than you can with physical information. I'm not saying it's the same as that, but there's weird phenomena when you look at wave travel and propagation. Yeah, I don't know, Jim, if that helped answer. I think
I think you're saying
sorry.
that the rotation of the galaxy isn't just a bunch of stars moving around. It's a wave that's actually happening here. I think I have to leave it at that.
yeah, I think so. The thing is yeah, you have to look at if you have a like let's look at our sun for instance, right? That's just one object. It's going to go around at a certain rate, but the whole arm itself moves in a different kind of way. And it's no matter where you're at on that arm, it's spiraling at the same, and it has to do with this wave theory.
Weird. Okay.
So I had always thought that the difference in the speeds was because as the arm goes around, some stars burn out and some stars come into existence, possibly on one edge or the other, but not necessarily in the center. And so even though the stars uh, may be going one speed, the appearance of the whole looks either greater or less. Is that something like what this wave compression theory is?
Um, it's pretty complicated. It could be some of what you're saying. I don't know if I fully understood everything you said there. I uh think of it as, you know, like I've heard of this, they talk about like this compression business happening. Um, you think of it as just like a section of higher density moving, but the objects themselves they're not traveling. It's just like they bunch up on one side, it gets high density, and then as the wave pushes through, these particles fall out, and then it's compressing back on the other side, right? And so you just have this constant compression, expanding, and then the wave is moving, but not the objects themselves. They're moving at the normal angular momentum based, orbital kind of speed. Does that help?
I think Belinda, you had a question. You had your hand raised. Let you unmute.
Thank you. Yeah, I have two questions, but the first one that I have is, okay, so these findings highlight the remarkable set of conditions that make our galaxy's position and structure uniquely suited for life. So from your perspective, what are the main scientific arguments offered against interpreting this as evidence of intelligent design? Or like say when you present this kind of information to your fellow scientists in this field, what is it just maybe they hadn't really thought of it that way? And is this more like just kind of an opening to have that conversation or?
Yeah, I think honestly that's a hard thing. I haven't spoken a lot of different people. You know, most of my like friends or coworkers that I know they are believers, and they see of course the universe is designed in a certain way, but from a scientific perspective, um, I think some of these can easily be could I could see people saying, hey, these could easily be explained by natural processes, and um, but it's only after you show a bunch of these factors, right, where people always start like the light bulb kind of goes, and then they're like, well, I don't have a good explanation, but they're not willing to take that next step, right? Because in the end, it's not hard data, right? It's so you have to show it's more likely that there's design here than that's a better answer than like just natural laws or chance or something. And so if you can demonstrate that, um, you you have a better case. Now, a lot of this stuff's not quantifiable, right? Like a lot of the things I showed tonight are just, and Hugh Ross in his books often says just to write this or that, and then you need this to happen. But there are papers in some of these cases where you can show that these really are life permitting or excluding. But that's a lot of work, honestly, to build up the case. Um,
So it's a cumulative case then,
Yeah, I think that's the
that
best
again.
way is
Okay.
you have to, like any one of these on their own, doesn't prove one way or another, but it is interesting. Uh, because let's say the number really is 7% of the Milky Ways are like ours, and only that means only 7% of all the spirals or of those 7%, you know, only life can be in those type of galaxies, right? Well, that's a very broad statement. I mean, no one's going to believe that on the face value. Then you'd have to start showing them like all these other conditions, right? I didn't talk about like the barred spiral shape. Maybe it doesn't need to be a barred spiral. Maybe it just be a regular spiral. But uh, or maybe you're not at the co-rotation, right? We find a lot of planets. Most of them aren't at the co-rotation distance. Uh, So there's a lot of work ahead of us too to sort of narrow this down. But I think, yeah, cumulatively is the only way to really make a convincing case.
Okay, now for the person that's just a amateur astronomer, just stargazing and such, and say like I'm sitting there with them watching these stars. Um, what aspect of our galaxy's fine tuning would you say is like an oh wow, that's a very interesting point kind of thing to maybe just even get them started? And hopefully they won't ask me any more questions beyond that because I'm sure I have to just point them to, to your website or something.
So you're asking like what of the
Like
galaxy
a
fine tuning?
excuse me?
Are you asking like what of at a galaxy level, what is the
Or,
best?
like I'm just sitting with somebody looking up at the stars and,
Yeah.
want to start a conversation, but not too deep from my part because
Well,
I won't
I,
understand a lot of it. But
yeah.
if they might know a little bit more, like what would be like you think would be a good statement to share with them about, oh, these stars, instead of just saying, oh, these stars look amazing. Like,
I've spent a lot of time with looking at the Kalam cosmological argument, and that's just the basic question of that there's because most people are fascinated, right? Like we actually had a public star party there, and people come out and for the first time they see all the stars, and so when they're doing this, seeing the all wow and the magnificence of that, that's a good point time to ask about, well, uh, how do you think this all came about, right? Or just some lead in to see kind of where people are, and if they're open to the idea, you know then you can pull something like the Kalam to say, hey, things just don't come out of like there's a reason why there's something rather than nothing, and there
okay.
has to anything that comes into existence like our universe with all this magnificent beauty and all that has to have a cause, and we have a lot of evidence that our universe was caused, right? And we can talk about uh, you know expansion rate and the cosmic microwave background, right? You have all these backup tools, and so that works really well to at least get people know that there's something beyond our universe that caused our universe.
Okay.
And then if you know some of the fine tuning, you can make it more personable, if you will, for life. And it's a task, but astronomy is an easy way to start those conversations. I've taken my telescope out to parks, and they're like, "Hey, what are you looking at?" You know,
Uh-huh.
I mean, people, it's a magnet. People come up to that, and it's a good conversation starter.
Okay, thank you.
Yeah, commenting on that, I've had discussions where I kind of asked, why do you think there is anything? And people come up with all kinds of reasons, but eventually you can push them down to a point where they say, well, we don't know where everything came from. There's no reason. It's just the way it is. And kind of my response at that point is to say, well, if there's no reason underneath everything, and yet science is based on reason, you've just thrown out everything that science is, because we're saying everything it's based on doesn't have a reason itself. And it can get into a kind of an interesting conversation.
Yeah, yeah,
Um,
I could see that. Yeah, I think in those kind of cases, I would also bring up, um, if there's no explanation, it just is. Well, why isn't there other things that are like if they're kind of implying if things can pop into existence on its own or something, that should be happening all the time then, or why haven't we
yeah,
seen anything else? Or it just goes against common experience. But um, yeah, that kind of branches into a lot of philosophical discussion at that point.
right.
Yeah.
Yeah.
And it,
I
it
was
really
on,
depends, yeah, on the people, how willing they are to think about these too. Some people just like to brush it off, like, hey, it's too complicated, it's just the way it is, and they don't want to think further.
well, at some point, it just comes down to an uncaused cause for everybody. Um, I
Yeah,
mean, that's inescapable, you know.
yeah.
On the spiral arms, I was wondering, is there a density difference between the mass that's on the outside of the spiral and what's in the center? I mean, the stars traveling on the rim of the galaxy are traveling faster to keep up with rotation than the material in the center too, right?
Yeah, like if we're a star orbiting, right, it's really just kind of it, it's not exactly all the mass is concentrated at the center, but it's almost like that, right? And so it's just like Earth orbiting the sun, right? There's like Kepler's third law, right? Um, in a sense, but the density wave theory, I know this kind of going back to Jim's question. It it's not like think of the wave as traveling through the material, but it's not. Um, it's really hard to explain. uh, the way it's the same along the whole arm because it's the wave propagating at the same rate, and so on any given arm, or I believe this is the case. I could be wrong, but I think along the whole arm, it's just it's all connected in the sense of a wave pushing through in a circular motion. So whether you're closer in or not, I don't think that makes a huge difference. But I think there could be a difference there. I'm just not totally sure on that. But I think um, the if you did, I wish I probably should have pulled up. There's if you look on the YouTube, there's some computer simulations from some of the schools where they show you how the wave propagates without moving the particles. It's really just it makes it look like the arms are moving, but it's really I mean the arms eventually move because the particles themselves are rotating, but the wave um, has to do with this compression and constant compression and decompression as it moves as the wave propagates like radial or circumferentially around.
Should be like a
It's probably not
wave on the
answering your question.
surface. Be a wave on the surface of a body of water. Like a wave can travel across without actually displacing water and moving it
Yeah,
along.
kind of like that. Yeah, I think it's kind of like that. Yeah, and
Hmm.
yeah, that's probably a closer example, I think. I don't personally study this type of thing, and I know it's relatively new, and they've had some. Uh, it's only just a theory at the point as far as how the spiral arms move differently than the actual objects in the arms.
Yeah,
So
was
it's
just
still kind of.
one more
Yeah, go ahead.
one more comment. I was just thinking it like going through the different levels, like starting with Earth, going to the solar system, then the galaxy and clusters, super clusters. They're all fine tuned. The fine tuning in the at the finer levels are actually contingent on fine tuning on the next higher level and on up. I mean, you just can't get away from it. It's like there had to be fine tuning
Yeah.
at the beginning to get fine tuning down through all of that.
Yeah, that's true. That's one way to look at it. It's all related. Yeah, like for instance, if you weren't a spiral galaxy, then you would be able to say, have a co-rotation radius, for instance. Right? Yeah, that's a good point.
I was just going to mention that if anybody wants to see your earlier lecture 6 or 8 months ago, it's on our website, and it's up on YouTube. But the easiest way to find it is to go to ssreason.org/events, and you're listed right there.
Okay, thank you.
Oh, okay.
I have another question. Raise another challenging topic. You mentioned very briefly dark matter, and what are the thoughts in terms of stabilizing spiral arms or other structures of galaxies?
Well, I mean, that's the common theory. That's really how dark matter was first sort of discovered, in the sense that there's got to be more mass than what we visibly see in galaxies by looking at the rotation of objects radially outward. And so now they have lots of pictures of dark matter halos and things like that. So the question is and they can measure it through the mass, estimating the mass and things like that. So they know there's something there. And I'm familiar with, like, there's an experiment called alpha magnetic spectrometer up on the ISS, the International Space Station. And so back in the 1970s, right, people were on paper looking at dark matter candidates. I'm not sure if they called it dark matter then, but in particle physics, there's coming up the math and the theory allows you to predict other particles. And so that's like how, like the Higgs boson, for instance, right? I'm not saying that's dark matter, but they, took that one step further. So these, what we now call like neutralinos and axions and things like that, there's whatever those features are of those particles. When you do the math, they make predictions on, like, if these interact with each other, they produce secondary particles, and we can detect those. And so there's been a lot of experiments out looking for these sort of inferring these secondary particles. And the AMS has been measuring now for almost 15 years, and they're actually upgrading it to get a little bit more statistics on it before the end of the life of the station. But they're pretty close to making a concrete discovery to say they've confirmed this dark matter signature, or they've discovered some new astrophysical phenomena, but it matches pretty much exactly the theoretical predictions that these types of particle interactions shouldn't exist. And so I think, there's a lot of evidence for it, and it's just a matter of time and that's not the only experiment. There's a lot of other experiments looking for that. Randy, what was the part of that question? Did I answer that?
Oh, yeah, I've just the stabilizing the spiral arms, the dark
Yeah,
matter.
Yeah. Okay. So, yeah, I mean, that's what's, there's some mass out there, that's that's the idea. That's the only explanation they can come with, that there's just more mass out there, and that would explain perfectly the rotation of all the objects at every distance. And so I don't think anyone doubts that. They're just like, they don't know what it is, right? That's what they're trying to find out.
Okay.
I was just going to point out, Hugh Ross, when he was talking about galactic positioning of where we are in a galactic arm, he pointed out we're also positioned exactly in a place where we don't have, where we can observe what's going on in the universe. We don't have too much material between us and what's out there to interfere with being able to observe and test and come up with theories. So you've thought about that also?
Yeah. Well, they're real big on pointing out our we live in a unique time and place, really a time in the history of our universe because of the expansion rate, and being on the scene, 13 billion years later. Given the rate that's already taken place, we still have the ability to see all the way back to the C and B. Is that what you're talking about? Like that,
Yeah.
like the full history of the universe as far as we can see. Probably even more so if you factor in gravitational waves, we can see probably further back than that. And I think there's more research to come out on that. But if we came on the scene, let's say, I don't know, a million years later, on a 13.7 billion years, a million years later is not like a huge difference. But if we did, maybe we wouldn't be able to see the CM or the formation of stars or things like that. But right now we can look back and see pretty much everything in the history of the physical universe.
Yeah, it's pretty amazing.
Yeah, it really is.
How much, and maybe this is not answerable, but how much of the universe is actually visible to us, and what sort of horizon do we have?
I think so. That's actually a question that there's probably some variations on the answer. I know I haven't done it in a while, but when you looked on Wikipedia the master of all sources, if you if the universe wasn't expanding, and let's say it's 13 billion years old, right? That means if you look in one direction, you can only see as far as 13 billion years because that's how long it took the light to reach us. And if you look the other way, so you can only see a 26 light year sphere around us, right? But when they factor in the expansion rate and it's accelerating, I think the number is closer to 1,000 light years. I mean, I'm sorry. Maybe it's parsecs. I'm always getting the units wrong. But yeah, instead of 26 billion light years, I might double the age of the universe. It's more like 1,000 is what I've heard. But it's just I don't think anybody commits to that. But the problem is we don't know if it's infinite, right? Like if it's the extent of how massive it is. There's some experiments out looking at the curvature of the universe, and that's if you look at some of the Planck satellite data, that's one of the really weird measurements they try to make, and how flat it is determines, if it's flat versus curved or not, concave or convex, right? That a lot of people were looking at what does that mean on the fate of the universe and will it keep expanding forever, or will it reach a maximum and contract, right? That's pretty much been eliminated, I think. And the numbers like 2 or 3 decimal places of being purely flat as best they can measure, which tends to tell you it's going to continue expanding all the way and stop expanding right when it ends, or whatever that is, at infinity, right? But those are still a little bit speculative, but the numbers seem to be confirmed over and over again, maybe just being refined a little bit through some of the measurements.
Other questions? Anyone on Zoom have a question that wants to ask? Or do I see a hand raised? Just go ahead and unmute yourself and. Cliff, is that you? Okay. Yeah, you're still muted. Still muted, Cliff. While Cliff is working on that, anyone else have a question?
Okay, I'm sorry, I had the wrong speaker set up.
Okay, you're on.
Yeah, okay. Yeah, so I had just it might be kind of a silly question, but I know when water is swirling. Okay.
I'm sorry. Can you hear me now?
Yes, yes.
No. Okay, so I got to go back.
No, you're good.
Yes.
We can hear you.
Okay. You can hear me. Okay.
Yep.
But now you don't hear the echo. So here's the thing. Okay. When water is draining out of a tub, it spirals. And if you're in the southern hemisphere, I'm told it goes in one direction. But if you're in the northern hemisphere, it goes in the opposite. And I've always been curious, these spiral universes, why do they spiral in the direction that they're doing so? Do we know what causes it?
Yeah, I think well, so like the bathtub problem is really well known because it's tied to the Coriolis force on Earth, right? Because of the Earth's rotation. But in space there's no direction, to be honest, right? I mean, whether it's clockwise or counterclockwise, it depends which way you're looking at it. But what kicks it off is same thing with solar systems. When they condense, right? Gravity's pulling things together, and wherever there's more mass on one side or not, starts that rotation. And then once that happens, it's fixed, right? And so that's just the convention. It's an angular momentum problem on how things begin to rotate.
So they rotate in different directions all over the universe?
Yeah, yeah, yeah. Because
Okay.
yeah, it's really yeah. There's nothing. They're all positioned in different locations and different angles. So it's just it's if you could statistically look them up, they'd all you'd have 50% clockwise versus counterclockwise, but that's an irrelevant term because that doesn't mean anything because you can look at it the opposite side and give it the same number or the other number, right? And so yeah, it's kind of a weird
Yeah, it's
one.
all direction.
Yeah,
Yeah.
I do. Hey, I do. While I pulled this up, let me just share one last thing. I probably should have put this in the talk, but look, if you got it, just 2 minutes. It's a video on. All right, do you see a spiral here?
Yes.
I don't know about the audio. Let's try it out, but this explains a little bit.
You are getting sleep.
That's Twilight.
We don't hear any audio, but we are seeing the video.
Are y'all seeing it?
Yes.
Okay. So the picture here, right? If you did not have the density wave theory, it would look like it is on the left, right? And so what she's trying to show you is what the real case is on the right here, if I can get it going again.
Mm.
We're brainwashing you. You will donate.
Oh boy.
Oh, look at that.
Interesting. Oh. Okay.
There you go.
That's cool.
So like on this video, I could back it up just a little bit, but if you pick any one of these dots, it doesn't follow the arm. It's still moving in a circle around on the thing. It's this compression of the wave as it propagates that makes it look like they get closer together as the wave passes through, and that keeps this shape of the arm here. But once the wave passes through, the object's still moving in its normal circular motion, and the wave looks like, kind of rotates away from it. Does that make sense more?
Interference pattern.
Kind of, but it's let me back it up. Just if I'll play it one more. I don't know how big it is, but I can post this link too. I mean, there's a few of them on there. If you do, just pick one of these dots once the waves are established here, and you can see it.
Red or something.
They should have put 10 green dots in.
Like, look at the dot right here. Look at this guy, right? It's moving. It's right there. It's right there. See, it's still moving around like that. So it's a pretty strange topic because it's kind of hard to visually it's kind of hard to visually see, but hopefully that helps.
Well, it helps confuse us, but I would appreciate that.
Yeah, it's it's not intuitive, but there's nothing really. I mean, it'll make sense once you see it if you actually watch these.
Yeah.
The individual particles still go like this. It's just the wave they're constantly being squeezed together, and visually when they're clumped together, it makes it look like the arm's moving, but it's not. It's just a wave pushing through.
I guess my question is, what's the energy force behind the waves? What creates the waves?
It's that's a good question. I personally haven't studied it, but I think it has to do with when you have lots of, in this case, here they're doing particles, right, that are interacting. It has to do with gravity, and things kind of clump together, and once that starts happening, combined with the individual particle motion, it just starts developing that way. I don't know how to. I guess I don't have a better answer, but it has to do with the way the gravity, because it's called density wave. It's also called gravity wave models, right? It's weird because it's a circular motion kind of thing too, which isn't really easily visualizable. But yeah, I would just suggest researching it some, but it's it's still active area of research, but that seems to be the best explanation for how the arms rotate differently than the actual stars themselves in this case. And I think it's applicable to other ideas that this is modeled on.
Well, thank you.
It looked like there was, they introduced a little bit of eccentric motion in the center of those circles. Once they had that disturbance, then the waves started to form. So maybe.
Yeah, and I'm not sure, how they started it. They don't go into the details on their computer model. I mean, I just picked the shortest one for this kind of thing, but there's a few more out there that explain in a lot more detail.
It just looked like it jogged the center a little bit, and that set things in motion.
Yeah, they had to twerk it to get it going. I think in reality, related to that other gentleman's question, is why does it go clockwise versus counterclockwise, right? That's just purely a like a gravitational contraction, and it just really it's a anisotropy of the mass distribution that causes that initial rotation, and then once it starts going, because of gravity pulling it in, it just feeds it, and then it picks up. You can't reverse it at that point. And it's the same thing with the solar system. Yeah.
Yeah.
Go ahead. I'm done.
Well, thank you very much. You're in Houston, so you're 2 hours ahead of us. So thank you for your time and your expertise and the great presentation and all the extended Q&A. I'm curious. You mentioned a third talk. What do you talk on besides these two?
So on this one, I had read a few papers. So at Johnson Space Center, there's a little side research organization called the Lunar Planetary Institute, and that's the group of people that study all the like the Apollo rocks and things like that, and they're looking at the early solar system formation. And I went to a talk that inspired me to read a couple of their papers from other places too. And the question was, there's evidence of our early solar, like when you look at the smallest particles in our solar system, they're dust grains. There's features of those dust grains that seem to indicate like our solar system wasn't formed where it currently is. And then I remember Hugh Ross had he had highlighted a few articles on these papers, and so I started reading them. And the idea was one of the explanations of why we have higher metallicity in our solar system than where we're currently predicted to have based on our distance from the Milky Way galaxy is that it was formed earlier in and somehow it got perturbed and pushed like to where we are now. And so that's what the topic was, is to there's a little bit of chemistry involved. I'm not a chemist, but there's a little bit of that in there, but there's some really unique things that go into looking at how our solar system may have formed early on from a globular cluster, a very dense cluster, and they got kicked out. And there's a lot of science that supports that kind of idea through several different papers. And so that's what it's about, is looking at our birth solar system cluster being somewhere closer in and how we got positioned here, perhaps.
Okay, another very interesting topic. Thank you. Again, thank you so much for your time and your expertise. We really appreciate it.
My pleasure.
And,
hey, great questions from everybody, and it's my pleasure. So I liked it.
Thank you so much. Yeah, and next month we're excited to have Dr. Belinda Calabia, who's with us tonight actually on Zoom, and she'll be speaking on the case for life, and it's basically how to winsomely and effectively discuss the abortion issue. So we're looking forward to Belinda's talk next month, and we will be sending out an announcement as well. So again, thank you for coming, and I wish you all a good evening.